I'm Albert. I do cryptography research at Nethermind. It's a pleasure to be here and present our work on implementing lattice-based folding schemes. So this talk was supposed to be given by Ilya Vlasov, who led this implementation effort, but unfortunately he could not make it, and I'm here in his place. Okay, so let's give a bit of background and notation for those who were not Dan's talk. So in folding, we have two instance witness pair. There's an interactive protocol between a prover and a verifier, and you reduce two instance witness pairs to a third one in a way that if the third one is valid, then the initial two ones are valid, except with negligible probability. Commitments are very important in folding schemes, and in general, all commitment schemes contain the instances contain commitments to the witnesses. So these pairs in here, they look like this. So the instance has an actual public instance and then a commitment to the witness. So this blueprint in here looks like this, really. You always have the commitment to the witness in the instance. And usually the commitment is homomorphic, which means that the commitment to the sum of two witnesses or vectors is the sum of the commitments. That's not always the case. There's some work where researchers are trying to avoid using homomorphic commitments. For example, the ARC scheme, where the commitment scheme is Merkle tree commitments. Okay, so in general, commitment usually is the Petersen commitment or a KZG scheme or something similar, something based on elliptic curves. So most of famous folding schemes are based on this type of commitments, but there are some drawbacks. One drawback is that these commitments necessarily work over large fields because you need an elliptic curve. So the scalar field of an elliptic curve, if you want it to be secure, it must be relatively large, at least 250 bits. The commitment can be quite expensive, especially if the vector has large entries. So if you want to commit to a vector with 250 bits in all entries, then you're in trouble. It's quite expensive, as I will show later. And also, this commitment is expensive to recurse over, so proving statements about operations between these commitments can be expensive because of foreign field arithmetic that appears when you arithmetize elliptic curve operations over a field. So here we analyze an alternative which is based on lattices. So we work with cyclotomic rings, which are rings of this form. So you take ring of polynomials with coefficients in a field and you quotient it by a cyclotomic polynomial. For example, x to a power of 2 plus 1. So as I said, this is just the set of all polynomials of degree at most less than d. Then there's a very interesting isomorphism. So this ring has an interesting algebraic structure. It's isomorphic to the direct product of several copies of a field extension of FQ. The number of copies and the degree of the extension depends on the prime and the cyclotomic polynomial you choose. And this is quite interesting in terms of performance because it allows to pack field elements into ring elements. So if you have tau field elements, which might be tau witness elements, so tau field elements from a witness, you can pack them into a single ring element. You simply put the tau of them, one in each component of this direct product, and then you take the inverse of the entity, and you get a single ring element. So each ring element can potentially encode tau field witness elements, or for example, tau trace cells in an error trace. And we will use this, we will rely on this a lot when assessing the performance of lattice-based folding. Okay, so what are I-type commitments? The parameters are just a matrix which is randomly sampled with entries over the ring. And the matrix has dimension kappa times n, where kappa is certain parameter, and n is the size of the vectors you want to commit. So in this commitment scheme, you commit to vectors of size n with entries in the ring, and the commitment is just the multiplication of the matrix by the vector. And of course, you get a vector of kappa ring elements as a result. there's a big caveat in this commitment scheme, which is that it is only binding if the norm of the vector you are committing to is at most b for a certain parameter b, which is roughly 2 to the square root of kappa, if you fix the rest of parameters. And the norm of the vector is the largest coefficient of an entry in the vector when you see the elements of the ring as polynomials, which you can always do, right? So because this commitment is only binding for vectors whose norm is at most b, we can only use it really for vectors whose norm is at most b. So we have to add this clause to the input. Okay, so what happens if you want to commit to vectors that have large norm? Well, what you could do is you could decompose the vector into several chunks, with each chunk having norm at most b, and then you commit to the chunks. So there's a trade-off between the number of rows in the matrix, in the itai matrix you use to commit to vectors, and the number of chunks you need to split a vector of arbitrary norm into. So because b is 2 to the square root of kappa, if you want to have matrix multiplication that's very cheap, by having a small number of rows, you get a smaller b, which means that you have to decompose your vectors into more chunks. If you are willing to pay more when you commit by increasing the number of rows, then your b is larger, which means that you can use less chunks in here. So there's this trade-off. In some cases, you have that v has low norm in a natural way. For example, there's LatticeFold Plus, this recent lattice-based folding scheme from Bonnet and Chen, where a very important step in this scheme, and maybe the most expensive computationally, requires committing to vectors, all whose entries are powers of x. And these vectors have norm 1. So for these vectors, one can potentially use an itai commitment matrix with a very small number of rows. Okay, so another issue that comes with this norm restriction is that the commitment scheme is only homomorphic in some sense, right? It's clear that if you commit to the sum of two vectors, you have the sum of the commitments, but maybe the sum of the two vectors is out of the range where you can commit to. So it's technically not an homomorphic commitment scheme, though it does look like this and it's almost homomorphic. On the other hand, there's very nice things that come with itai commitments. One is that you can take a small field, for example, a field with 32 bits or 64 bits, including star primes like the Goldilocks prime or the baby bear prime. As I said, each ring can pack tau field elements, so you can pack several field elements into a ring. The commit computation should be easier to arithmetize over the base field than Pedersen commitment, because the operations you are making are these ring operations which are quite natural over the base field FQ. It's plausibly post-quantum secure, of course, and commitments with itai with this scheme can be cheap, as I'll discuss next. Okay, so let's choose I'll present some numbers now, and I'll choose the following configuration. So we take the base field to be the Goldilocks field. So the prime is about 64 bits, and we take the cyclotomic polynomial to be this degree 24 polynomial, and then you can see that this ring, if you configure it this way, it splits into the direct product of 8 degree 3 extensions of FQ. And we take kappa, the number of rows in the itai commitment matrix, to be 10, and this forces us to take a norm bound of size 2 to the 8. So recall the itai commitment scheme. There's a matrix. The commitment is just multiplication of the matrix by the vector. So if we try to if in our implementation, committing to a vector of size 2 to the 16 costs 76 milliseconds. And recall that a ring element in this configuration stores 8 field elements, right? So committing to a vector of 2 to the 16 ring elements can be, in some applications, the same as can encode a vector with 2 to the 19 field elements. So in this case, we would be able to commit to 2 to the 19 field elements in 76 milliseconds. On the other hand, because the norm bound is 2 to the 8, if we want to commit to a vector of arbitrary norm, we would need to split the vector into 8 vectors and commit each vector separately. And in this case, we would need to pay 8 times 76 milliseconds, which is about 0.6 seconds. So if we want to commit to a vector of low norm, the cost is 76 milliseconds. It commits to the 19 field elements. If the norm is large, then the cost is half a second. It commits again to the 19 field elements. Here we assume that the vector is given in entity form as well as the entries of the matrix. And this is kind of a cheap assumption because computing entities turns out to be relatively cheap. And okay, so now I'm going to compare these commitments to the cost of committing with Merkle trees. So here there's in each row there's the cost of computing a Merkle tree commitment to vectors of different size using different hashes for the Merkle tree. So again, I'm going to compare the cost of I committing to 2 to the 16 ring elements with the cost of committing to 2 to the 19 field elements because of this ring packing technique I explained. And also, I'll compare 2 to the 16 to 2 to the 19, but also it might make sense to compare it to 2 to the 20 because when you commit with Merkle trees, you usually commit to an encoding of the vector, and the encoding is larger by the rate of the code. So it might also be reasonable to compare 2 to the 16 to 2 to the 20. Okay, so what? Sir? Yes. Yeah, I'm going to compare the two scenarios. Okay, so if the vector has small norm, then it's about 2 times faster than Merkle tree Ketchak, comparing 2 to the 16 to 2 to the 19 or 2 to the 20, depending on whether you want to multiply by the inverse of the rate or not, the blowout. And it's much, much faster than committing to Merkle tree with Poseidon. I'm not sure, actually. If the vector has large norm, the commit time is half a second. It's about up to 3 times lower than committing to Merkle tree with Ketchak. And still, it's much faster than Merkle tree Poseidon. And then if we compare the commitment cost with Pedersen commitments, we have the following. So again, I'm comparing 2 to the 16 to 2 to the 19. If the vector has small norm, it's between 7 to 30 times faster than Pedersen. So here there's a big difference. The Pedersen cost is very dependent on whether your vector has small entries or large entries. If it has, so the difference between committing to a vector with small entries and a vector with large entries with Pedersen is about 10x. If the vector has large norm, then it's either 2 times lower than Pedersen or 4.3 times faster than Pedersen. Okay, so now I'm going to talk about LatticeFold. So LatticeFold is a folding scheme for CCR relations written over a cyclotomic ring. It uses I commitments, and it consists of 3 phases. There's the linearization phase, which is analogous to the linearization phase in hypernova. There's a phase called decomposition, and then there's a step where you enforce the norm bound I mentioned that you need in I commitments. And this is, in the LatticeFold terminology, this is called the folding phase, but here I'm calling it norm bound enforcement. So regarding the composition, as Dan explained, I hope, to fold 2 witnesses, so the folding in LatticeFold is done as usual, which is you take the 2 incoming witnesses and you try to take a random linear combination of them. So the problem with doing that just out of the box is that maybe the norm of your witnesses is larger than B, even if your original witnesses had smaller norm. And you don't want, so this cannot happen because then the resulting itai commitment is not binding. So the solution proposed in LatticeFold is to split the vectors, the witnesses, into chunks of small norm, and then commit to them and take a random linear combination of these chunks, having one random challenge per chunk. And the random challenges are sampled in certain set so as to ensure that when you combine all the chunks with these challenges, you get something that has norm at most B. So again, in the same configuration as I said before, and taking witnesses of size 2 to the 16, the decomposition cost in LatticeFold in our benchmarks is of 3 seconds. In LatticeFold, and this comes from the fact that you have to split the witnesses into many chunks. In this setting specifically, each witness is split into 8 chunks. So in total, there's 16 chunks, and in this step, you have to commit to 16 vectors. And this 16 commitment cost adds up to 3 seconds. In LatticeFold, the decomposition step is done at the end, and LatticeFold Plus, sorry. And LatticeFold Plus manages to do it to only commit to 2 chunks, no matter in all cases. And so I'm going to, in this talk, I'll give some numbers on LatticeFold Plus performance. This is it's not, we haven't implemented LatticeFold Plus. I'm just extrapolating them from parts of our implementation of LatticeFold. So these are speculative numbers that are extrapolated from our benchmarks for LatticeFold. So the expected decomposition time for LatticeFold Plus is less than half a second in this configuration. Okay, regarding the norm-bound enforcement, so again, in general, when you fold 2 witnesses, you want to take a random linear combination of them. The problem, if you just do this, is that you want the extractor to output witnesses with norm at most B. But if you just take a random linear combination, this is apparently not possible. Well, there's no apparent way to do that. And the way this is solved in LatticeFold is by adding a range check during the folding step. And this range check is expressed by means of a grand product, which is then reduced to claims about evaluations of multilinear polynomials via sum check. So, and there's one range check. So the range check is performed by running a sum check, and there's one range check per chunk. So in the configuration I mentioned before, I said that each WI has to be split into 8 chunks. So there's 16 sum checks, 16 range checks being proved at each folding step in LatticeFold. So the cost we get for this step, this range check enforcement is 3 seconds with the same configuration as before. LatticeFold Plus, the main contribution of LatticeFold Plus, in my opinion, is a new way to add a range check during the folding step, which is much cheaper because first, it requires running as many sum checks as the degree of this quotient polynomial, but the sum checks happen over the field. They happen over FQ, not over the ring. And yeah, yes, extrapolating some of the costs of running sum check over the ring, which is basically running the cost of running 8 sum checks in parallel because of the entity decomposition. I estimate that the cost of LatticeFold Plus, the cost of this range check for LatticeFold Plus, shouldn't be more than 1 second. Okay, and the linearization step is not very special. It's just the same as hypernovas. You just run a sum check on the CCS relation to reduce it to a set of claims about multilinear evaluations of multilinear polynomials on some random points. Our benchmarks are that this costs 170 milliseconds. This is a a negligible part of the cost of LatticeFold in our experiments. And in LatticeFold Plus, this should be exactly the same because it's the same step. So overall costs for LatticeFold to fold 2 instances for a CCS witness of size 2 to the 13 with the configuration I mentioned, which means that our witnesses have size 2 to the 16 because we have to split the, so if your CCS witness has size 2 to the 13 and you want to commit to the vector, you have to split it into several chunks because of the norm bound restriction I mentioned, because that's what I explained. If you want to commit to a vector of arbitrary size, of arbitrary norm, you have to split it into chunks and commit to the chunks. So here we have to split it into 8 chunks, right? Because the bound is 2 to the 8. So we are working with witnesses of size 2 to the 16, really. Or if you want, 8 vectors of size 2 to the 13. So the cost of linearization is, well, these are the costs I mentioned already. In total, this gives 6.17 seconds. This is the extrapolated cost of LatticeFold Plus in the same configuration, which is about 1.17 seconds. And then regarding Hypernova, taken from the Sonova implementation, committing to CCS witness of size 2 to the 16. And here I put 2 to the 16 because a vector of size 2 to the 13 in this configuration stores 2 to the 16 field elements. The cost is 1.2 seconds. So conclusion, LatticeFold is relatively more expensive than Hypernova. I don't know if it's too much expensive, not too much expensive. I'm just presenting the numbers. LatticeFold Plus seems competitive with Hypernova, but these are preliminary numbers. We'll see what happens once it is implemented. And oh yeah, and then I wanted to mention this new folding scheme by Nguyen and Sethi, which looks very promising, and we're also very excited about analyzing its performance. And that's the end of the talk. So if you are interested in seeing a very detailed report of our benchmarks, you can check this link. And if you want to use our repo, our implementation, and all the tools we built for lattice-based cryptography, you can follow this link in here.
I think you're one of the first that didn't caveat the repo with, hey, we're cryptographers, don't use it in production or something.
Yeah, please don't use it in production.
Oh, okay, okay.
So I'm curious why you picked 24, 8, and 3, because of course the 8 relates to the K, which relates to the amount of, the most costly thing there is the norm bound and the decomp. So you could basically reduce that by, for example, 12.2 would seem to reduce both of those costs. And again, 24.1, so why those choices?
In these benchmarks, we made a grid search of best parameters possible. And for LatticeFold, we found that this configuration I shared is one of the best. And so I presented the results for this one. And it's quite difficult to predict which one will be the best without actually running the numbers because there's so many parameters. It's possible that for other schemes, like LatticeFold Plus or NEO, other configurations of parameters yield better results. We'll see. In here, there's actually quite an extensive grid search of parameters.
So we're a standardization event, and every time someone shows up with something new, we try to figure out if there's going to be a new and a new, which means that it's not time to standardize on this yet. Here you have LatticeFold and LatticeFold Plus. Would you say that it's an open field of research to find more optimizations?
I would say that yes, yeah, I believe so, because LatticeFold is maybe 1 year old, and LatticeFold Plus and NEO just came out. So, and LatticeFold Plus and NEO introduce at least LatticeFold Plus introduces very significant improvements, in my opinion, to LatticeFold. So I think it's very early to start standardizing.
For sure, early to start standardizing. The question is, should we expect, I don't know, next year? This is one of the leading post-quantum schemes that that are out there, right?
Yeah.
Okay. More questions? Okay, thank you very much.
Thank you.